This module is about linear scale conversions, where we will determine equations that allow us to convert from one scale to another. This important skill is useful when we program PLCs, and it's also useful when we troubleshoot our analog signals out in the field. In the example on the left, we have a conversion between 0 to 20 milliamps and 0 to 50 pounds per square inch gauge. The x-axis represents the original units, and the y-axis represents the units that we will convert into. We can look at the graph and guess for any given milliamp signal what the PSIG level would be. However, if we want accurate results, we need to calculate it. The example on the right shows the familiar conversion between degrees Fahrenheit and degrees Celsius. Unlike the example on the left, this conversion does not begin at the origin point, so we will have to address the y-intercept. Returning back to our milliamp to PSIG conversion, the first thing that we need to determine is the slope. Intuitively, we know that the slope is the ratio between the ranges of the two scales. We calculate the slope as the scaled range that we want to convert into divided by the original range. Scaled range is the maximum scaled value minus the minimum scaled value, which in this case is 50 PSIG minus 0 PSIG. The original range is 20 milliamps minus 0 milliamps, or 20 milliamps. This gives us the ratio of 50 PSIG for 20 milliamps, or 2.5 PSIG per milliamp. Keeping track of the units will allow us to do some cross-canceling and double-check our results. As I mentioned before, this example has a y-intercept of 0, which we can plainly see on the graph. This gives us a final equation of y equals 2.5x, so let's plug in some numbers and see what kind of results we get. For an x value of 5 milliamps, we have y equals 2.5 times 5, which is equal to 12.5. The milliamp units in the numerator of the x value and the denominator of the slope cancel to leave us with a final unit of PSIG, the unit we intended to convert into. If we plug in a value of 15 milliamps for x, then we multiply 2.5 by 15, and that gives us a result of 37.5 PSIG. For our temperature conversion example, we can follow the slope down as we reduce x, going from right to left, and we can see that the y-intercept will be a negative number on the degrees Celsius scale. So for this problem, we're going to need to calculate both the slope and the y-intercept. This slope is the scaled range, 100 degrees Celsius minus 0 degrees Celsius, divided by the original range, 212 degrees Fahrenheit minus 32 degrees Fahrenheit. Performing the subtractions, we get 100 degrees C divided by 180 degrees F, which is the familiar ratio of 5/9 degrees C per degree F. Calculating our y-intercept, we must consider both the scaled minimum value, which supplies a direct offset in the y-axis, and the original minimum value, which must be converted using slope. The value for y-intercept b is the scaled minimum minus the product of the original minimum and the slope. For this conversion, we don't need to concern ourselves with the scaled minimum, though, because it's 0 degrees C that our scale starts off at. So to calculate our y-intercept, we multiply 5/9 degrees C per degree F by the original minimum of 32 degrees Fahrenheit, and that gives us approximately negative 17.778 degrees Celsius. If you want to keep this number as accurate as possible, then keep the fraction of 5/9 rather than converting to decimal. This gives us a final equation of y equals 5/9 x minus 17.778 degrees C. If x equals 50 degrees Fahrenheit, then y is equal to 5 over 9 times 50 degrees Fahrenheit minus 17.778 degrees Celsius, which is equal to 9.999 C if we use the decimal approximation for the y-intercept. Some of you might be aware that 50 degrees Fahrenheit is equal to 10 degrees C and wonder why we're off by this small fraction. The difference lies in rounding error in the difference between the decimal approximation of our y-intercept and the fractional exact number for our y-intercept. When we display this number on our operator interface terminal, we're likely to be rounding it off to a number of specific decimal places. But if our PLC were to, for example, be sounding an alarm when we reached 10 degrees C, then it would be important to make this calculation as accurate as possible by using the fraction rather than a decimal approximation that uses fewer digits. Many of you are already familiar with the conversion equation between degrees Fahrenheit and degrees Celsius, and you might be wondering why we didn't subtract the 32-degree original range minimum from the temperature in degrees Fahrenheit before we applied the slope calculation. Mathematically, they are the same thing, but in many scale conversions we will not have a scaled minimum that is 0. In those cases, we could bring the original minimum inside of the parentheses, but we would also have to make sure that we captured the influence of the scaled minimum. In our last example, we have a 12-bit signal inside the PLC, 0 to 4095. This output produces a 4 to 20 milliamp signal that controls a 3 to 15 PSIG I2P controller. What pressure should be present at the I2P output port when the PLC output is set to 1500? Here we're discussing three different ranges, but all three ranges are 0 to 100% representations of the same signal. So when we want to convert between any two of these, we don't need to convert to each step in the linear progression of how the signal travels. We can perform a single conversion from the original range we want to begin with to the scaled range that we want to end with. In this case, converting a 0 to 4095 raw value signal into the 3 to 15 PSIG output. I'm assigning the arbitrary unit of measurement raw value in order to be able to track the units as we complete the conversion. Again, we calculate our slope as the scaled range divided by the original range. 15 PSIG minus 3 PSIG gives us a scaled range of 12 PSIG. We divide that by the original range of 4095 raw value, and that gives us 1 over 341 1/4 PSIG for each raw value. For the y-intercept, we have 3 PSIG that's contributed from the scaled minimum. With an original minimum of 0 multiplied by any slope, we get no contribution from the original minimum. So therefore, our y-intercept is 3 PSIG. When we plug in our 1500 raw value, our calculation yields a pressure of 7.4 PSIG.